Okay, so today the goal is to learn things about unbalanced optimal transport. Okay, so here are some original references. Probably John David Benamo started the discussion about unbalanced mass transport. Then later, the main reference for us are these, I think these four works, especially these three. And they, so Riero, Mieke, and Savare, they defined the so-called Hellinger-Kantorovich distance, which are now sometimes called Wasserstein-Fischer-Rao distance. Okay, and then these papers developed some theory about that, and now it is being applied in many directions, I think. Okay, and for preparing this lecture, I use these three sources as my main references. Okay, and I think this article is very well written, and this one is a lecture slide from this Kantorovich Initiative Summer School, given by Gabriel Pere. But just be careful that this lecture note has some typo. Okay, so you have to take it with grain of salt. And Giuseppe Savare also gave a seminar talk in Kantorovich Initiative a seminar about unbalanced optimal transport. This one is kind of much more thorough than this lecture note by Gabriel Pare. Gabriel Pare's note has many images, which illustrations, which will help us to understand the theory. But Savare's one, probably it gives more details. And this one gives some nice review of this unbalanced optimal transport. And in below, the theorems I state are given without citation. Okay, so I just assume that they are from some of these source articles. Okay. Any questions so far? Okay, let's start with it. So what should be unbalanced optimal transport? So optimal transport itself, it gives a kind of matching between priority measures. And features of priority measures, I mean, probably the most important feature of a priority measure is that its total mass is equal to 1. So optimal transport, the usual ones are given on these measures with the same total mass. But of course, then as a mathematician, you may want to consider a more general case. Okay, what if the mass are different? The total mass are different. Like one measure has total mass 2, the other one has total mass 1. Then what should be the a proper way of matching them? And then, of course, an easy answer is that you just normalize everything with two priority measures. That's the point of view we have taken so far. We can just normalize any measure, any positive measure to a priority measure, then we can do optimal transport between them. But maybe this is too simple, and maybe it does not help in some context. Okay, so we simply want to ask what should be the proper distance between measures when they have, in general, different total mass. Okay, just feel free to stop me if you have any questions. Okay, and regarding such context, consider, for example, this figure here. Here you want to, let's say, okay, we have two distributions, this purple one and this kind of yellow one. Okay, just assume that they have total mass. Maybe the number of points are the same. But then here, if you do optimal transport, then these nearby ones are kind of matched together. Okay, not this. These nearby ones are not matched, but this one is matched with this, and this one is matched with that, and this matched that, and then this one is matched with this. But then maybe some of these paths are kind of outlier. I mean, let's say these point clouds are from sampling two distributions. Okay, but the sampling may not represent the ground truth very well. I mean, in general, right? Especially if the sample size is not large enough. Then some of the also the from the sampling or even the from the let's say if these data are given by experiments, then some of the data points can be just obtained with some error because of error, right? So then, for example, who knows? This one can be just due to such error, okay? And then we may call them outlier, okay? But then maybe you don't want to match these. Then in fact, if you do the proper unbalanced optimal transfer matching, then you don't match these, okay? But you match only these, okay? Sometimes this is desirable because these are nearby distribution points. So maybe you want to match this, but these are kind of far away from these cloud. So you just want to leave them.
So we just want to match. So for those lines that are matched, they also preserve the same mass, right?
What is sigma?
Yeah, I mean those lines that they are matched connected.
Yeah, these lines indicate the transport plan. I think so. Yes.
Yeah. Can I say that in advanced OT you're doing okay? We just try to match transport those that are very close to each other, and then for those that are far away, we ignore it. So even though mu and nu have different mass, we just transport those that are very close to each other.
Right. So there's one such feature, but another thing is that actually, I mean, you can just you can ignore this, but also another way to view this is that instead of kind of transporting this mass, you can just do some kind of teleportation between them. So you just you can match them. Okay, but here, I mean, when we draw these arrows, then the matching cost is maybe is some function of this the length of these kind of line segments. Okay, but then these are too far away. So here, matching them, I mean, considering this kind of cost from moving here to there, maybe it's not reasonable. Then maybe there should be some way to measure some kind of teleportation between these. Okay, and then we can then in that sense we can match all these unbalanced purple points with this unbalanced this distribution of purple points and these yellow points. Okay. Am I making sense? Any questions from the Zoom? So here, so unbalanced mass transport is not only for measures with different mass, total mass, but even in the space of priority measures, okay? Some definition of unbalanced mass transport may give you some different way of transportation, okay? Or different way of matching. Some things are kind of transported to the others, but some paths are kind of teleported.
I have a question.
Yes.
How does this fit in the outlier detection literature? Is this a good way to detect outliers? If we had a way to detect outliers before,
yeah, that's a very good question.
We use this before and then?
Yeah. So the question was, does this unbalanced mass transport help to classify outliers? Possibly, but frankly speaking, I don't know the literature very well. So maybe you want to search for it. Okay. Sorry, I don't. So basically, I don't know, but
Okay.
probably. Okay. But one thing, one hypothetical example is this: you have, let's say, some kind of shape. Okay. Let's say from some imaging. Okay, and but some information, let's say here, is missing, and then you have some kind of samples here, another samples, and you want to match these two distributions. And if you do the usual optimal transport, you may just match these points in here, missing this part. But maybe unbalanced mass transport may still kind of fill this kind of missing part. Okay. So in unbalanced transport, I mean, we want sometimes some kind of freedom to transport somewhere where the target measure is not supported. Okay, not only into the support of target measure, but also sometimes outside of the support of target measure. So that's what I wrote here. Yes.
Think about the unbalanced optimal transport. I think of two situations.
Yes.
Where the target that you are mapping from has more mass than the target measure.
Uh-huh.
And the second situation is where the target measure has more mass than the target that you are mapping from.
Right.
So these two situations are both considered by optimal transport or just one?
So the questions are there are basically two situations where the source measure has larger mass than the target measure, and then, or the other way around, the target measure has a larger mass than the source measure. Of course, these two situations are symmetrical. I mean, you will see. I mean, it should be symmetrical because you can just consider them, one of them as your source and the other one as your target. So yeah. So that can be that's a kind of typical situation, but also an example of this unbalanced transport is so-called partial transport. Let me just mention it here. Partial transport. So it is a bit different. It is kind of similar here. Okay, you do not necessarily match all the mass. For example, but so let's say you have in one domain you have some kind of mass here, and in the other domain some mass here. Okay, then of course, I mean, you can scale and you can match everything. And in the unbalanced mass transport, we consider we kind of match basically everything. Okay, including this like transport and teleportation. But sometimes in the context of partial transport, what you do is you just match, let's say, only some portion of the mass. Okay. Okay. Also, other motivation is if you consider, let's say, for example, evolution of distributions, like in biological models. I mean, you can view organism as a collection of cells, and this collection of cells change over the time, but you have a birth and death of the cells, okay, reproduction and death of the cells, and then the population of the cells may increase or decrease. So naturally, that dynamics does not, I mean, it's not the dynamics of probability measures, okay? Am I making sense here? Any question? Okay. Okay, then what should be the idea? Okay, so the optimal transport, probably I mentioned this maybe in the earlier lectures. it's kind of horizontal analysis that given mass distribution like this one and this, the way it matches these two distributions is that you kind of try to move the mass on the space. Okay, so then this mass, if you can just consider, for example, this kind of dynamic version, then this mass is transferred to the other one just by moving the mass. So that's what optimal transport does. Okay, philosophically. But then, of course, in this way, because of mass conservation, you don't create this. You cannot match this distribution with different total masses. But then, one way to handle them is just increase or decrease the mass. Okay, and another extreme kind of trend of matching is like teleportation. Namely, okay, this is your let's say mu, and this is your nu. Then teleportation is like this. So how do you match these two? You just decrease this mass and just increase this mass there. Okay, you move this and then you just put them there. So this is like teleportation. I just call it like a vertical analysis. You just move vertically in a way. Okay. So then the idea of unbalanced mass transport is to combine this transport and increase and decrease of mass. In other words, you just combine this horizontal and vertical analysis together. Okay, that's kind of the main idea of the whole whole business. Okay. Okay, then. Okay, we know optimal transport. We know this like horizontal way of matching things, but what should be this kind of vertical way? So to understand that, we want to consider some kind of cost for or some kind of measure comparing distributions in a vertical way. Okay. So let's say we now have just set of positive measures. So unbalanced transport gives a matching between measures in this space. And then in the following, I will just consider some general class of such kind of metric comparing two measures in a vertical way. So let's just pick some convex function on positive real line. Okay. And let's say phi 1 is 0. Okay, this kind of normalization. And this is nothing but the asymptotic slope of that function. Okay, as p goes infinity. So for example, if the function looks like this, then the slope of this is exactly this. Okay. Okay, then what do I do? What do we do? So then C just, probably my pronunciation of his name is not correct, but C just phi divergence is defined in this way. So given two positive measures, you define this phi divergence between alpha and beta in the following way. So here beta becomes the reference measure, okay? So it's basically this formula here. For the moment, you can ignore this, okay? You just consider this Radon-Nikodym derivative between alpha and beta with respect to beta. Derivative of alpha with respect to beta, and then just apply phi there for this value, and then you just integrate with respect to beta. Okay. And your favorite entropy function or Ki divergence belongs to this class. Okay. And where this came from? So it is this. So if you take the Radon-Nikodym derivative or Radon-Nikodym decomposition of alpha with respect to beta, then you have this absolutely continuous part and singular part. Singular, absolutely continuous with respect to beta, and this alpha pulp is singular part of alpha with respect to the beta measure. And then basically, this alpha pulp is where this one goes to infinity, okay? But then if you just look at this formula, as this one goes to infinity, okay, if you divide it by, if you just consider it this way, if you this divided by d alpha and d alpha, then this whole thing looks like this phi p divided by p, where p is d alpha divided by d beta, okay? So as this one goes infinity, this whole thing will converge to this phi prime infinity, okay? Then there you just consider the corresponding part here on those singular part of the on the singular set. So that is what happens here. You just have this value and this. Okay, am I making sense here?
No, I didn't get that.
Okay, then that is your exercise. Here, then let me. I'm just explaining where this came from. Okay, so try to just apply this formula. Okay, by itself with some measure, and then just regard this alpha pop as the part where d alpha d beta goes to infinity. Okay.
Mhm.
So far, so good.
And y infinity would beta be zero there?
Yeah. Sorry. No. The singularity is kind of defined that way. So the singular part is where this derivative is basically infinity. I mean, intuitively speaking.
Okay.
Okay. So then you can just rewrite this as d alpha d beta and d beta d alpha and d alpha, right? And this part is phi p divided by p equals d alpha d beta, right? Okay.
Okay.
And then on the singular part, then there is a singular part, right? On the singular part, this one, this p goes to infinity. So this whole thing will converge to this.
Yeah.
So you have integral phi prime infinity and the alpha, but on the singular part, on the singular set. So then this is constant. That's why you have this. Okay. Get it?
Yeah.
Okay,
Thanks.
good. All right. So good. So here, this alpha and beta in this definition do not necessarily have the same total mass. Okay. They are just partial measures. All right. Okay, so that is the definition of phi divergence, and then KL divergence, Kullback-Leibler divergence, or sometimes called relative entropy. In this context, you can just slightly modify the expression, but essentially it's the same expression we saw in the Kullback-Leibler divergence. So the function phi is this one, s log s minus s plus 1. So this function looks like this phi should look like, so in S, so it should be when S is 0, it is like 1, and when S is 1, it's 0, and it should look like this. Okay. And this asymptotic, there is no asymptotic slope. Sorry. So the slope goes to infinity. That's why you have that. Okay. Okay, then this KL divergence, I mean, in this context can be written in this way. And you see, if you consider probability measures, KL divergence between probability measures, then of course this cancels out. So that is exactly the same formula as we saw before. Okay, making sense? So this, when alpha is absolute continuous spectra, you have this formula, but otherwise you have the kind of positive infinity if this is not absolute continuous, because in that case, phi prime is infinity. So if alpha is not absolutely continuous, then that infinite part dominates. So this K divergence will be infinity. Okay, KOA divergence is infinity if alpha is not absolutely continuous with respect to beta. Okay, and another interesting such divergence is the so-called total variation. This is basically L1 norm, okay, but between measures. So you have in this case, phi s is this s minus 1. So it's basically, it looks like 1. It looks like this, right? So this is the phi. And then this phi prime infinity is just has this slope, which is equal to 1. In this case, you can just compute. Okay, so this is your exercise. To verify such phi divergence with this phi gives this total variation. Okay, you just regard this signed measure, and then the total mass of the signed measure is this total variation. And there's another formula for the total variation. So you can view this one as kind of because it's like L1, so it's like a dual of L infinity. That's why you have this formula. Okay. But there are other such phi divergences. Okay. And all such phi divergences have this property. Because of this convexity, you have this joint convexity of this d phi. And
That's for any phi?
any phi with this property, convex. And because of this phi 1 is equal to 0, when alpha and beta is equal to each other, then this phi divergence is 0, and vice versa. This is like a non-degenerate. Yeah, so it's positive. So here I should be careful. So this should be like you need some kind of strictness here. Okay, so it is the function maybe I should put only when s equals 1. Okay, then with that kind of correction, I think this is true that if this is 0, then they have to be equal. So this phi divergence gives some kind of it's not exactly metric because you may not have this symmetry or triangle inequality, but it gives us some kind of a measurement how different the two measures are. And the reason why I call it a vertical analysis is because what you just compare is just it's kind of this kind of ratio between the density alpha and the density of beta.
Excuse me, Professor.
Yes.
So when we talk about the convexity of this divergence functional, when we mention convexity, we are mentioning these types of like teleportation of convex combination. Like we're just taking convex combinations.
Yes. Yeah. So this is
measures.
convexity means just you view this alpha and beta as just a vectors, and then you just do this summation and scaling, the usual convex combination in a vector space.
Right. Okay.
Okay. And I should okay. I just remind something, but I forgot what was it. Oh, okay. Maybe I important. This phi divergence does not depend on the metric of x. Okay, because this is just basically a pointwise comparison at each x. There's no like comparing the mass at different locations. Okay, just at the same location, you compare the mass. Okay, so it does not depend on any like geometry on X. Okay, making sense?
A quick question. So if we ask about the displacement convexity of this functional, like actually using the Wasserstein, if we restrict the probability space and ask about the displacement convexity,
Yeah, of course, you have it, for example, for Ka divergence, right? You have some kind of displacement convexity of that Ka divergence, right?
wouldn't that depend on the underlying metric of the manifold or underlying, like we're talking about?
Yeah, so that geodesic convexity certainly depends on the underlying metric because this geodesic depends on the underlying geometry.
Right.
But
Okay.
I'm just
And so-
saying the value of this functional has nothing to do with the geometry, the value itself. But when you consider,
Right.
okay, I mean, you raised a very good point. But when you consider this geodesic convexity, you are studying this function in terms of certain geometry. Then there, of course, things will depend on the geometry. It's like gradient flow. I mean, the function itself can be it's just defined without any reference to the geometry, right? Let's say a function on Rn. You don't need any metric to define a function. But when you talk about gradient of the function, you need the reference metric.
Right. That makes sense.
Yeah. Okay, but that's a very good point. Thank you. Okay. Then, okay, how do you combine this horizontal and vertical analysis? So let's say this phi divergence gives some kind of horizontal analysis, and then we have this optimal transport cost respecting this kind of vertical analysis. Then how do you combine? We just simply add these two. Okay, that's how they did. Okay. So this is the formula to define this unbalanced optimal transport between these two positive measures. So you have this, excuse me, this transportation cost part for some transport plan, okay? But this transport plan may not match these given marginals because the transport plan, what is a transport plan? Or between two measures. You have some measure in the product space whose first marginal is the given first marginal. So its first marginal is one of the given measure and its second marginal is the other measure, right? But then the thing is that to have such feature, those two measures, let's say mu and nu, have to have the same total mass. But of course, not in our case. So this transport plan cannot match these given marginals. No transport plan can match. But then the idea is that, okay, we still consider the marginal. The first marginal pi1, the second marginal pi2. I mean, the marginal means they are just the push forward by the projection mapping of that measure pi. Then we just compare these marginals with pi with this given mu and nu, given source and target distribution. Okay? So it's kind of relaxing. Can view this as a penalty term for pi not being a transport plan between mu and nu. Okay? So if phi was indeed a transport plan between mu and nu, when mu and nu have the same total mass, then these two terms will go away, then you just come back to the ordinary optimal transport. Okay. Right. And another point is that even when this mu and nu have the same total mass, okay, depending on this balance between this phi divergence and the transport cost, your pi may not match these mu and nu. Okay. Who knows? There's just making this unbalanced. I mean, not matching this mu and nu could be. Could cost here, but it may reduce the cost here. Then this unbalanced transport may prefer that. Okay, so it may not necessarily match mu and nu as the marginals, even if mu and nu have the same total mass. Okay, if the transportation cost for doing that is relatively larger than just sacrificing not matching these source and target measures. Okay, so we have a lot, much more flexibility here.
Can you remind me, I just have a technical question about the mass of the marginals. So if we have a measure on the product space, and we know the total mass of this pi and the measure on the product space, what can we say about the mass of the marginals?
It's the same as, so basically the marginals is, you can imagine, okay, maybe let me draw something. So you have a product space that's an X and Y. Transport plan is some kind of measure here, okay? What is marginal? Okay, just treat this each point as a drag. You just project it down, then you have the collection of the corresponding drags, right? So that distribution of drags is basically the marginal. So because of that, the total mass between this and this are the same.
Really? So the marginals have the same total mass as pi?
As the transport plan.
Okay, so pi 1 and pi 2 will have the same mass.
Pi 1 and pi 2 will have the same mass, yes. Okay, so that's a good point. Yeah. Note pi 1 and pi 2 have the same total mass as that of pi. Okay?
Thank you.
What is this M plus set?
Okay, this is just the set of positive. Positive means non-negative measures over X.
Okay, so there's absolutely no, in that set, there's no restriction on the
Total mass.
total mass. Okay.
Other question?
I do. Oh yeah, sorry.
Good.
So
Okay.
my question is, does this unbalanced OT problem has a dual form?
Can you just repeat, please? I just missed.
Does this unbalanced OT problem has a dual formulation?
Oh yeah, of course. Yeah, sure. And another thing maybe I should mention is that in optimization theory, okay, this is some kind of functional you want to optimize for this objective function, right? Your transfer plan is still an objective function. I'm sorry, decision variable. So pi is our decision variable, and this is the objective function. Okay, and basically there's no constraint except this pi being having this non-negativity, but also pi 1, pi 2 are given as the first and second margin of pi. So basically, this is the constraint. Okay, this is a constraint, and your decision variable is maybe you can just regard pi and pi 1 and pi 2 as your decision variables, and then this is your kind of function. The objective function, and and then minimizing that object function among this decision variable is what this unbalanced optimal transfer problem is. And when we consider an optimization problem, it is super important, but super important or super good, or if we have convexity of that objective function. In other words, if we do not have convexity of objective function, okay, then I mean, things are not as nice as having convexity. So what about this? This functional, do you think it is convex in terms of pi? Or pi and pi 1, pi 2?
I think it is.
Yeah.
So this is linear in pi, right? And then this one, if you go back, it's a jointly convex, right? So it's convex in pi 1, also in pi 2. So these are convex functions in the usual, let's say, vector space convexity. Okay, so the function, the objective function, pi 2 or pi 1, pi 2 to this CD pi plus d phi 1, pi 1 mu plus d phi 2, pi 2 nu is convex with respect to the linear convex combination. Linear means the convex combination in vector space. Okay. Is this clear now? I mean, this convexity. James? Okay, good. Any further question? Oh, sorry. Okay, you mentioned about duality. Okay, now because this function I is a convex function, okay, it's a convex minimization problem, and whatever constant you have, this is like a linear constraint or convex constraint. So basically, this whole problem is a convex programming or convex optimization, and convex optimizations have a duality.
Okay, thank you. Yeah, now I see why it has a dual form. Yeah, thank you.
Okay. Of course, what exact dual form it has is something we want to consider too, right? But at least it has duality. Okay, other question?
I have a naive question real
Yes.
quick. I don't want to take too much time, but why are we restricting to non-negative measures? Why not just any
Oh,
measure?
that's a great question. Yeah, maybe you can consider the more general cases. It's just because the focus is probably on. Okay, then you can even ask. Okay, in optimal transfer, why do we focus on priority measures, right? So that kind of question. The context you may apply the theory kind of is about non-negative measures. But of course, I mean, if you have different contexts, then maybe you may consider more general measures. Okay, at least this theory is restricted to this. Okay. Did I answer your question?
Yes, thank you.
Other question? Okay. Okay, what is the feature of this thingy? So here, if you do not have this thingy, then just you can consider kind of interpolation of these two measures mu and nu. Okay, this is mu, this is nu. Then you can consider interpolation, okay, like in geodesic interpolation. Let's just treat this whole thing as like a metric, and then you consider some kind of geodesic or displacement interpolation using this metric. And here displacement interpolation is like this. Let's L be basically this metric, this whatever this thingy here, okay. And displacement interpolation, you just consider this kind of Wasserstein barycenter between two, in this case, two measures, okay, using this one as your like a kind of distance square thingy. Then such thing in the two marginal case, two measure case is just this minimization. But let's just find that one among the probability measures. So this is just basically px. Okay. Then such displaced interpolation with respect to this look like this picture. So this is your mu, this is nu. The things in the middle for different t looks like for t is close to 0 like this, and then if you increase t, it moves like this, and this, and then finally this. Okay, so that's the feature of this unbalanced optimal transport. It is very different from the. Okay, it's not very. It's different from the usual optimal transport. If you do displacement interpolation between this measure and this measure, which is just translation of this measure, then the displacement interpolation is nothing but the translation. You just move. Okay. And if you say if these weights are kind of much bigger than this, so that you can ignore this, then if you only consider this, then such displacement interpolation is just this one. You just decrease this. So for example, if for some t between 0 and 1, what you have is your smaller mass here and then some mass there. Or maybe the total mass is like this and then this. Okay? That is what mu t is in this case. So here in this case, this is what mu t is. And here in this case, this is what mu t is, the displacement interpolation. Okay?
Does the cost C control how quickly that shrinks?
Yeah, so I think it certainly is related to the relation between this and this, okay?
Yeah, like the sort of linear, you could linear scale the cost. And
yeah, for example, you just scale this, okay? Then if the lambda goes large, that means this infimum we prefer respecting this more, then it should be more close to this picture. And if lambda is very small, that means you don't want, that means relatively, if you just normalize this, it's like a 1 over lambda here, right? That means if lambda is very small, then this one is very large. Then you want to avoid causing these quantities become positive. That means it goes to like the usual optimal transport, that is this picture. So their relative like strength will determine the kind of rate of your creation and annihilation of mass. But of course, this is just very like a rough statement.
Yeah.
Sorry, I think that it's the opposite way. If you put lambda in front of the cost, then it'll be more sensitive. For large lambda, it'll be more sensitive to the cost term.
If large lambda, did I say? Yeah, so I think I said the same thing. So if this large lambda, if this is very large, then that's the same as, let me correct it. Thank you. Now that is same as this, Okay. Then if when lambda is very large, then you can ignore this. That means you want to you can ignore this part, right? Because this one goes to 0.
Yes.
Okay, so I just got confused. Okay, just give me a second. If lambda is large, then it goes to 0. So then
Closer to the optimal transport to
I don't
is weak.
yeah, penalty is weaker. That means you don't have to pi is allowed to have different marginals than this given mu and nu. So this is more close to the unbalanced case. So then that goes to, I think, this. And if lambda goes to 0, then this penalty becomes very large. Then you really want to you want to turn this into 0. That is kind of the optimal transport case.
Oh, okay. Yeah, you're right. Okay, I think I was wrong. Thank you.
So whatever it is, okay. So now is everybody happy? I don't remember whether I said it correctly before, but anyways, okay.
Do we expect the optimal and transport plan converge to some sort of optimal transport plan when we almost ignore the last term, those divergence?
Maybe can you repeat?
I mean, if you scale those divergence terms and then you take the scale goes to 0, that's the distribution. If it exists, converge to the optimal.
Okay. So James' question is, let's say you may scale the problem like with this lambda parameter, okay, giving some weight on the penalty. Then you will have the solution pi lambda, the optimal solution. And then as lambda goes to, let's say, infinity, the problem will be, I mean, this one will be more sensitive, right? So then you will want to make the optimal transport between this. Okay, if lambda goes to infinity, if those total mass are different, right? Then maybe I should mention this. Okay, so consider UOT lambda is infimum of pi with lambda d phi 1 pi 1 mu plus d phi 2 pi 2 nu, right? So here, as lambda goes to infinity, if mu total mass is not equal, then let's call this C unbalanced cos C lambda. Okay, just definition. Okay, just notation for this. I just cooked off for now. Then this thingy becomes positive infinity, because if these are not equal, there's no way to make this 0. Okay, so then this is always positive. Then if lambda goes to infinity, this one will be infinity. Okay, now when they are equal, then if lambda is very large, then the transport will want to make this 0. Then you come back to the optimal transport. And James' question is whether in such a case, the transport plan pi lambda, the optimal transport plan between them, in the case when mu is equal to mu, then the optimal transport with respect to this total cost, whether it converts to the usual optimal transport. Okay, and I think it should be, okay, but I think I believe that they did some work, okay, but okay, I think it should be. Okay, at least there's no obstruction of having that. Okay.
Mu equals to mu in the proof, or they are different. I mean, the total mass of mu when you write the proof.
Hold on. But before that, I don't need to introduce this notation. Sorry. So UOT lambda. Sorry, what was your question?
We converge to the ultimate one, right? We still first assume mu and mu have the same mass, right? Out of the discussion.
Yeah. So if they are different, then of course there's no way to converging to the optimal transport, the usual optimal transport, because the usual optimal transport in that case do not exist.
Yeah. Okay. And existence of being or existence of primary series, existence of minimum in the unbalanced optimal transfer is also a hard problem, right?
You mean is it clear whether we have existence of optimal transport in the unbalanced problem? Yeah, that's actually a very good point. Okay, so what James is asking, okay, in the previous case when we consider existence of optimal transfer plan, we kind of use the okay, let's say the domain is compact. Okay, we use the property that the spatial probability measures on a compact domain is still is a compact in with respect to the Wixar topology, and the functional is continuous. We have compact set, so existence is okay. But here, this one, then you need to okay. So with respect to the sorry, okay, so here basically it's not okay. Spatial plans, okay, so that is still probability space on the product space, so it's compact. But then here we should consider instead the space of sorry, yeah, so still it's kind of okay, maybe sorry. So this pi belongs to, did I mention it correctly before? Yeah, to the space of partial measures on the product space. And here, if the underlying metric is as the underlying domain is compact, but then these positive measures, the space of partial measures is not compact because partial measures can go to infinity. It's easily, I mean, it's because there's no like a limit, right, of the upper bound or any like a total mass. But then if you look at this part, but this part, I think there should be some condition on phi, okay, so that try to avoid mass being too large, okay? Otherwise, you can just keep increasing your mass, right? But another thing to consider is because this mu and nu are kind of fixed measures, you cannot make this pi 1, pi 2 arbitrarily large in terms of density. So that kind of restrict the freedom of pi. So it kind of gives the compactness. Okay, so I still believe the compactness of this not this one is not compact, but this function will, I think, go to infinity if your pi will go to infinity. So that requires some kind of condition of phi. Okay, under that condition, appropriate condition of phi, for example, the entropy functional satisfy that, you can kind of prove that the minimizers still exist. So it's like this. I mean, your function on, let's say, Rn, I just consider Rd. Rd is non-compact, but if your function goes to infinity as you go to, as you go to infinity of infinity in Rn, then still the minimum kind of is confined in some kind of compact set, and so the minimum exists. Okay, so such a feature is called a properness. So if the function is proper and the domain is complete, then it's kind of similar to having like a compact continuous function on compact domain. So you have minimizer. So I think with appropriate condition of phi and phi 1 and phi 2, you have such properness, so the minimum exists. Okay.
So the last two terms will help us to make good properties of pi.
Yeah. So I think if this one is yeah, I think you need some condition on this. Yeah, these functionals are this is just continuous with respect to weak star topology. I think. Okay, I may be wrong, but there should be some continuity. Okay, whatever it is. Okay, sorry. Just a disclaimer. I'm not an expert of this phi divergence myself. Okay. Or even unbalanced optimal transport. I'm just learning by teaching it. So, okay. Okay, so then one of you asks about duality. Now, it is your nice exercise to do. Okay. So this convex optimization problem has its dual problem. So this infimum in the dual becomes supremum. And then what should be the dual variables, dual decision variables? So your function here, objective function is this. Let's say this is the primary objective function. This is the function of what? Function of pi, of course. But you can view it as a function of pi and pi 1 and pi 2. Now with constraint, pi 1 is a projection, first projection of pi, and pi 2 is the second projection of pi. Okay, so you can view this relation between pi 1, pi 2, and pi as constraint. Then this functional has basically three decision variables, okay, with these two constraints. Okay, making sense? Okay, then for your dual problem, the number of constraints is the same as, each constraint gives you the dual decision variable. So each dual decision variable corresponds to each of these constraints. So let's say this one corresponds to F, this one corresponds to G. Okay. Okay. And then the objective function here is related to the constraint of the dual problem. Okay. So once you treat this as constraint and then it has corresponding, let's say, dual decision variable or Lagrange multiplier F, this one gives you G, and then you can kind of do the similar things we have done before when we talk about duality of optimal transport. Do you remember that? So you can do something like this. You can do, so this problem can be written as infimum of pi still in n plus, okay? But pi 1, pi 2 also m plus x times x. And then of this thingy, right? CD pi plus d phi 1, pi 1 maybe maybe let me just write it this way. So this is integral phi d pi 1 d mu plus integral phi 2 d pi 2 d mu d nu. Okay, I'm ignoring the singular part here. Okay, and then when I free up this constraint, then you can add this Lagrange multiplier f times pi minus integral d pi minus pi 1. Okay, what I'm saying is integral fxy fx d pi xy y minus d pi 1 plus xx gy. Oh, I don't have space. Okay, you know what I'm doing, right? James, do you know what I'm doing?
Yes, you're
Yeah.
just adding the indicator functionals for the constraint.
Yeah, I'm just d pi 2y. Okay, so then I should change it, right? So this one should be inf n and plus sub over f and g. Okay. So this condition can be written in this way. So for the supremum over all f and g. So if this is not equal, then this supremum will be infinity. So it will violate. It will not be good for the infimum. So then, and this one gives the kind of hard penalty that this pi has to be projectional pi has to be pi 1 and so on. Pi it has to have pi 1 and pi 2 as its projection. Okay. So then after this penalty formulation of this constraint, you can do subinf exchange. Okay, at least if you get the heuristic idea, if you want to the idea, you can just change the subinf. Then you sub goes outside, the inf comes inside. Then you do shuffle things, and then in the end you will get this thingy. Okay, with this constraint. And this constraint is, of course, similar to what you see in. It's actually exactly the same what you see in the usual duality in the optimal transport. But here, because of this thing here, you have this phi 1 star and phi 2 star, which are the Legendre transform of phi 1 and phi 2.
You speak on maybe the structure of the optimizer, like if we have an optimal solution of this problem, what kind of optimality conditions does it satisfy with properties generalized from the optimal transport?
The optimality condition, it's a good question. It's like basically the complementary slackness is our optimality condition, right? So if you solve this dual problem, then this f plus g is equal to c. That gives you the support of the optimal transport plan, and
Okay, so this optimizer
and then
only
maybe
support.
one you want to ask is, do we have any kind of convexity of this phi and g, f and g and so on, right? The optimal solution of the dual, whether the optimal solution of dual have some kind of structure as we have seen in the Brenier theorem, right?
Right. So you're saying that these two potentials, F and G, the support of the optimal measure is on the contact set.
Yes,
And
right. So
then we
right,
want to
right.
ask about their structure.
So this context set will give you the this complementary slongness, give you the support of the transport plan. But that's kind of general thing. But then the more further structure comes from I mean, if you do not have this, then you have this the usual thingy, the C convexity of phi and G, F and G, this. But because of this, you have something, I think something else. But at least what I can tell is, if you're, let's say, if you just weight the phi divergence, I mean, for example, in the Ka divergence case, if you weight it with lambda, then as lambda goes to infinity, the thing should go to the usual dual of the optimal transport, because in that case, phi star will convert to just identity. So then this one will convert to optimal transport and things. But the more like a detailed structure, or given this phi 1 and phi 2, how exactly this F and G are looking like at optimality is something I didn't prepare. Okay,
Sure.
you can look at the literature.
Sure. I guess even more basic, intuitive question, or I guess not basic, but like, how do we interpret pi? Once we have the optimizer, how do we interpret it as some sort of like partial coupling between mu and nu, I guess?
Yeah, so that is a very good question. I mean, yes. So simply this pi. Maybe you're asking this thing is just by looking at the duality here, right? Why do you expect that the optimal transport plan given here, which is supported on this context set, give only partial transport in general, not the full transport? Is that your question?
Yeah, or even like once I have the pi, like how do I reconstruct those photos in the that we started with, right? The intuitive notion of like how do I intuitively transport some of the mass to mu to some of the mass of nu given some pi which optimizes this problem, right?
So that I don't think I can answer it clearly now because of my lack of knowledge, but something related is this. So you can consider entropic transport, okay? You just add this entropy term, okay? Here, this entropy, or Ki divergence term, is with pi, okay? And mu times nu, okay? So they actually did this, this like a regularization in the literature. Then you can consider this. Then if you look at the survey paper of Perret and others, or even, yeah, especially the survey paper of Perret and others, they consider this kind of synchron algorithm of solving this entropic unbalanced optimal transfer problem, and you can just do some kind of algorithm, you can find it. And the key underlying fact they are using is this duality here, that this infimum problem has this supremum problem. Here, there's no constraint here, but you have this additional kind of functional of the duality, okay? And the point is, there, the optimal plan is given exactly as this. If you find the optimal solution for the dual, F bar and G bar, then this is exactly the same formula we have seen in the entropy regularized optimal transport, right? So you can characterize exactly your pi bar by knowing F bar and G bar, okay? And this will give you all the information where to transport or not, and so on. Okay? With this epsilon. And then to understand, to answer your question, maybe you try to find the case when epsilon goes to 0. But here, this F bar and G bar, of course, depends on epsilon, sorry. Okay. And then there you can see those the features at least as a limit of this. But I don't think this is a perfect answer, and whether you can just out of this optimal solution, there should be some clear way to say, or at least clear way to say, if you can determine at least theoretically some part where the mass is transported and where the mass is not transported, but it can be also like this. So here, if you look at, let's say, there are some cases. Okay, in this case, in this picture, okay, this is not okay. You have this, and in between you have something here. I mean, okay, maybe forget about this picture. What I meant is even okay, maybe here. Between this, some portion can be transported and also can have this teletransportation. I mean, it's not like you may not have this clear cut. There are some part is transported, some part is not. What I'm saying is the support of pi can be everywhere here. Okay? Possibly. We do not have in general pi transporting only like these locations, and these locations is not. I don't think it's necessarily true. So pi may transport everything here only partially, and then how much of it maybe okay. It depends on the all the other things, the divergence and the relation between the divergence and C and so on. Okay. Okay, so my time is almost the end, and so in fact, I prepared up to here for the Monday's lecture. Okay, now I spent a lot of time yesterday preparing the remaining part, but now I can cover only this part. Is it lecture 24 or 25? I think 25. 25. 25. 25. Yeah. Yeah, whatever it is. Okay, whatever it is. Okay. Okay. Thank you for your attention. But there are also this dynamic formulation of this thingy and also others. But my slide maybe is not that understandable without any further explanation. So if you are more interested in this aspect of dynamic formulation and even this kind of conic formulation, you want to look at where is it? These references, maybe this one together with this, okay? And Sabare's slide, maybe it's not so easy to digest, but it has very thorough explanation if you check carefully. But also this review paper gives you some kind of nice perspectives on things. It's not detailed, but it's very nice. Okay, so now it's time to go. Okay, thank you for your attention. So now we have one more lecture on Friday.
Sorry for asking so many questions. I wanted to just
Hold on.
say, like,
Can I just stop recording? Okay.